Today we're going to be talking about the shapes of molecules, and I always think it's nice to start talking about them in the context of a molecule we've already been discussing. So let's look at acetone. So if you're looking at acetone, you're going to see that there are several types of carbons on here, and the first of which have hydrogens bound to them. And I want you to recall that carbon has four atomic orbitals. And how do you make four bonds when you have two electrons in the 2s and then one each in a 2p orbital? So another way of phrasing that is, are all these bonds different? Is there one bond where you have full electrons coming from the carbon and none coming from the hydrogen? Others where they're fully from the hydrogen and not from the carbon? And the answer to that is no. They're actually shared across all these orbitals. And Linus Pauling was a Nobel laureate in chemistry, and one of his answers to this problem was that you mix or hybridize the orbitals. So we don't have to look at the mathematics of how these orbitals are hybridized, but roughly if you take these shapes together, you put them into a blender, and you come out mathematically with mixtures or hybridized orbitals. So if you start with four orbitals, that is the 1s, or one of the s orbitals, it happens to be a 2s orbital, and the 3 2p orbitals, you end up with four orbitals. So the way these hybridization math works is that you start with four orbitals, you get four orbitals out. You should always be getting the same number of orbitals out as you put in. And so when you put 1s and 3p together, you get a new type of orbital, that's a hybridized orbital called an sp3, and there are four of them, all at degenerate or the same energy level. And so it's important to recognize that these new hybridized orbitals have the components of the orbitals that came into them. And you can even figure out energetically where they would fall on a spectrum. So if you go from low energy S to higher energy P, these sp3 orbitals would exist closer to P than to S. And you could say there's about 25% S character and 75% P character. One way I like to think about this is if you have sugar and flour together as separate entities, and you can mix them together in different ratios, that a new concoction that you can make is going to have a kind of a component of both in them. So let's look at the shape of sp3 orbitals. So again, you take your s orbital and three of these p orbitals. The three p orbitals are all facing in different directions, or are all orthogonal to each other, and you end up with four new orbitals that have both s and p character to them. They end up having kind of this big lobe, and that lobe is effectively where you form the bonds. And there's this little tail at the end of these orbitals as well, and that's simply because they came from p orbitals, so you have to have that kind of p component to them. And now if you look at how these four orbitals are oriented, they are oriented such that there is about 109 degree, roughly 109 degree angle between all these orbitals. And so if you're looking at this drawing, the way that we represent these in organic chemistry is that if these lines are drawn as simple lines, you can think of them as being in the plane of the page. So they're all in the same plane. 1, 2, and 3 are all in the same plane. You see this orbital, or this bond coming out toward 3. This is, we call this a wedge, and it's coming out of the board at us. And this is a hash, and this is going away from us. And this is an important representation to practice. You can make a model and look at this yourself. And we call this overall orientation a tetrahedron or a tetrahedral geometry. So what about that central carbon, the one that is bound to oxygen as a double bond? Well, it's only bound to 3 other atoms, so we're not going to have 4 orbitals to bond with. We're going to instead use 3, and so we're going to hybridize 3 of these orbitals. We'll take the s and we'll take 2 of the p orbitals, and when we do that, we create a new type of orbital called an sp2. And again, sp2 has a component of the s and a component of the p in it. And you can say that there's a 33% s, because that's 1/3 of the sp2 is s, and 67% p. And so energetically, it is a little bit lower in energy than the sp3, but it's higher in energy than s, lower energy than p. The other thing to keep track of is that we have one leftover p orbital, and that one can just be carried over, and we'll see what to do with that one later. So again, if we now mix the s and the two p's together, we end up with 3 new orbitals, and you'll note that these 2 orbitals are both in the same plane. So if you think about this as this page as like a plane of paper, they both happen to be on the same plane. When you mix these 3 orbitals together, you have about a 120-degree angle between them, and so we call that trigonal planar. And if you now look at the remaining p orbital, that one is orthogonal, or 90 degrees, to the other orbitals that we've been looking at. So if you rotate this structure onto its side, so now this dotted representation is supposed to look like a piece of paper, you can recognize that this new p orbital would actually stick up and down out of the plane of the paper. So now let's look at that leftover p orbital. So that leftover p orbital is not going to interact with these sp3 carbons, because all of the p character in those sp3 is already spent. There's no more p orbital left to interact with. So it's going to interact with the other atom on this molecule, that is oxygen, which can participate in by donating 1 electron in a p orbital. And so when you do that, you can recognize that each of these atoms is going to be donating 1 electron into a p orbital, and for now I'm just going to have them at the same energy level. And when 2 p orbitals interact, they can form a bond, and they can also form, as we looked at before, an antibond. The antibond has a node in it, and I'll point out that we call this a pi bond, or sometimes we'll refer to it again as a double bond. We've heard that before. This is a pi star, or an antibonding orbital. That is, if you were going to add more electrons to the system, that's where they would go next. And sometimes a node is hard to think about, and what does this even mean if it's a node? So when these two are shaded together, that doesn't mean the electrons are where the shading is and not where the shading isn't. That's not what these orbitals represent. This represents an idea of phasing. And so one way I like to think about phasing is if you were standing up and trying to high-five someone. If you're always putting your hand up when they're putting their hands down, you are not in phase. But if you both have your hands up at the same time and down, or down at the same time, you could say you're in phase, and so you can have a productive high five. That's all for today, and thank you for your time.